In number 15 right here, we've got y over x plus x over y is equal to 2y. As I'm looking at this, I am pretty sure that we are going to need the quotient rule both here and here. Well, not pretty sure, definitely sure. And I think we can do it that way. It did occur to me to maybe try to combine these two fractions with a common denominator so that maybe we only need the quotient rule once, but that would probably require us using the product rule in the numerator, and I think we'd probably rather avoid that. So I'm going to go ahead and just dive into this one the way it's written, and we'll see if we live to regret it. So here we go. Quotient rule on the first term right here, guys. Our denominator, x, gets multiplied by the derivative of the numerator, dy dx, minus the numerator, y, times the derivative of the denominator, which is just 1. And all of that gets written over the denominator squared. So there's our first term's derivative. Plus, now we're going to do something very, very similar here with the second one. So looking now at this term, we're taking that derivative using the quotient rule as well. The denominator is y times the derivative of the numerator, well, that's just 1. So that's bottom times derivative of the top, minus the top, x, times the derivative of the bottom, which is dy dx, all over our denominator squared. That'll be a y squared. And all of that equals, and on the right side, the derivative of 2y, well, the derivative of a linear function is always just its coefficient, 2, but because this is implicit differentiation, we multiply that by a dy dx, and here we go. Now, that part wasn't too bad. The tricky part, I think, here is trying to isolate the dy dx. And the first thing that probably freaks everybody out right here is the fact that we've got complex fractions here. So what I think we're going to do is multiply both sides of this equation by the product of x squared times y squared. And what that's going to do for us, I think, is get rid of all the complex fractions here and make this thing hopefully a little bit easier to deal with. So if I multiplied both the left side and the right side here by that x squared, y squared, let's see what that'll do for us. Now I'm distributing this monomial into this binomial right here, and the first time I do it, the x squared is going to cancel with this x squared, but the y squared needs to get distributed here and here. So that's going to give us an xy squared multiplied by dy dx, and then a minus the y squared times y will give us a y cubed. Okay, that takes care of the first quotient that we had there. Plus, now when we go to distribute x squared, y squared into the second fraction, this y squared cancels with that y squared, but we're distributing the x squared in there. So the x squared times y is x squared y, gotcha, and then minus x squared times x is going to be an x cubed, and a dy dx at the end of that. The right side, fortunately, is much easier. Nothing cancels right here, so it's going to be a 2, and then an x squared, y squared, and a dy dx at the end of all that. Okay, now that everything is written on one line right here, it's probably time to count terms right here, of which we have 1, 2, 3, 4, 5 total, 3 of which contain the dy dx that we're looking for. This one, and this one. Now, I'm normally a fan of bringing the dy dx terms over to the left and everything else to the right, but since these two terms right here are the only two that don't contain a dy dx, and they're already on the left, it probably would be more direct if we moved this term over to the right and this term over to the right. So let's see what that does for us then. These two terms are going to be the only ones remaining on the left side, and I think it would be a little bit neater to write the positive term first. So I'm going to write that as an x squared y and then a minus y cubed, and that's it now for the left-hand side. Now on the right, I'm going to have my 3 dy dx terms. I'll start with the one that was already there, which was 2x squared y squared dy dx, and then the order here doesn't really matter too much, so I'm going to go with a minus xy squared dy dx. That was the original first term here, and now this guy, which was negative, is going to become positive when we move it over to the right side, x cubed dy dx. And now I'm going to do something that might annoy some of you guys. I'm going to try to combine two steps at once. I'm going to factor out the dy dx from all three of these terms and bring it out in front right here. And then I'm also going to divide by the trinomial that's going to be left over. And I think that's going to give us our final answer. So let's see what that would look like. Dy dx would equal, all right, the numerator here would be the original opposite side. That would be x squared y minus y cubed. And then we'd be dividing by the trinomial we get right here after we pull out the dy dx. So that would be a 2x squared y squared, and then a minus xy squared, and then a plus x cubed at the end of all that. The one thing, and I guess I do need to shrink this down a little, the one thing we want to watch out for now, is there anything that can be factored or canceled right here? And I don't believe there is. I noticed this term right here, which has just y's but no x's, and this term right here, which has just x's but no y's. That was the one thing I was looking for, and it looks like it didn't pan out. So that answer right there, I feel pretty confident in for our answer for problem number 15. Now, it would not shock me if you guys looked in the solutions manual and saw something that looked just a little bit different. So let's take a look. Their answer, as I'm looking at the solutions manual right now, is a y, and then in parentheses here we have a y squared minus x squared all over, and of course their denominator's a little more complicated. They factored out an x, and we're left now with a y squared and a minus x squared, and then a minus 2xy squared at the end of all that. So how does that compare to our answer? Well, if you were to distribute the y back in there in the numerator, you'd get, let's see, the y cubed and then a minus x squared y. It is the opposite of what we have up here in the numerator. Now that should concern you just a little bit, but look at what happens in the denominator if you distributed the x back in there. You'd get a positive x squared y, we have a negative x squared y. You'd get a minus x cubed, we have a positive x cubed, and you'd get a minus 2x squared y squared, we have a plus 2x squared y squared. Our numerator and our denominator are both the opposites of what they came up with. And when you have a fraction like this, where both the numerator and the denominator are the opposite of what you would expect, that's perfectly fine. It's kind of like if we were doing a slope problem, and I did it one way and got an answer of 3 over, let's say negative 3 over 7, and you did it another way and got positive 3 over negative 7. Your numerator is the opposite of mine. Your denominator is also the opposite of mine. Negative 3/7 is the same thing as 3 over negative 7. So when both the numerator and the denominator are the opposite of what they might have in their solutions manual, both of those answers are correct. They're mathematically equivalent, and there's no need to panic. There's no need to go back and change anything. We can express that answer in either of those two ways.